So my name is Perez Romero. I'm currently a postdoc in University of Nova Gorica, very close to here in the border with Slovenia. And I will try to summarize a bit the different works that has been done performing indirect dark matter searches in these objects that Viviana and Paolo were commenting that are Dwarf irregular galaxies. Okay. So, okay, I have a bit slides of introduction, but I try to be very brief because this has also been commented several times during the conference. All of the evidence that we have from the existence of dark matter comes from observations of astrophysics, and it comes from its gravitational interactions. And we need to take into account that these observations have been found at all of the different scales that we find in the universe, ranging from galactic scales, where we have the evidence from the rotational courses of objects, but also from the measurements of the velocity dispersions of terrestrial galaxies of the stars. At galaxy cluster scale, we have different kinds of observable proofs, like, for example, the peculiar velocity flows that were measured by Zwicky back in the days, for example, in the coma cluster, but also for different mass tracers that we have right now for measuring the mass of the cluster, like, for example, measuring X-ray surface brightness, for example, using strong lensing for clusters that are farther away. And also the puzzling systems like the one that I show here, which is the Ballet cluster. And of course, at cosmological scales, we have the evidences from the field of the decomposition of the anisotropies of the cosmic microwave background, and also the necessity that the formation of large scale structure triggers. And regarding this last part, I just want to briefly mention how we are going to consider this structure information theory that the lambda CDM provides to us. No? So in the standard cosmological model, or at least the most accepted one right now for the community, we expect inflation to see the perturbations in the field to create the curvature perturbation in which matter will fall and create the potential wealth. Then by hierarchical clustering, and meaning in a bottom-up scenario for structure formation, meaning the structures that will form first will be the smallest one, and then via merging, collapse, a bigger and bigger structure will start to form, and the driving component of all this process should be at least something very similar to a collisionless, non-relativistic dark matter, which we usually call as CDM cold dark matter. To be able to manage this whole process, we need to define fundamental units of cosmic structures, that is what we call halos, in which we expect the baryonic matter to gather and to form the actual structures that we are able to measure. However, we do not expect, according to this structure formation theory in lambda CDM, that all the halos are formed these big halos. No, we also expect some later halos to not be able to merge with the rest, and these smaller halos will end falling in the potential wells of the main halos. Then we will have this kind of hierarchical structure. We will have big main halos, and then a population of subhalos inhabiting all of them. And it has already been mentioned, with these evidences that we have from the observational measurements that we have, the amount of possibilities of proposing candidates to fit in the shoes of what we expect with dark matter is huge. There has always been the consideration of some requirements that in the last few years has started to be more flexible. Like, for example, I'm going to read here, we expect the dark matter candidates to be non-baryonic, and also we expect them to be electrically neutral, or at least for not being interacting directly with light, because this is what we see. Also, we expect them to be non-relativistic and collisionless. Again, these requirements in the last few years has started to become more and more flexible. And also we expect the dark matter candidate to be long-lived in order to be able to recover the observational results. So with this in mind, we see that there is a very long range of possible masses for the candidate of dark matter to be. Some of them we already have heard in the Congress. For example, fuzzy dark matter. It was I think there was few talks yesterday. Fuzzy dark matter usually have masses of the order 10 to the minus 22 electron volts. So they really behave more or less a wavy thing than a particle. And in the other part of the range, we find non-point-like objects, like astrophysical objects, like should be primordial black holes. And in the middle, we find weakly interacting massive particles. I'm sure that you already know, but the usual range of masses for WIMPs is between few GeVs and a few hundreds of TeVs. And they were thought to be extremely well theoretically motivated because also to be looked in the terms of astrophysical searches, because these weakly interacting massive particles should have been produced thermally in the early stages of the universe. So we can make use of this extremely very weakly, feebly interaction with the standard model particles to try to now get this kind of fluxes. So as Manuela was mentioning before, there are different kind of ways in that we can try to look for these WIMPs. But again, this talk is going to be focused on the indirect detection. In the case of indirect detection, just a very brief reminder, we want to focus in the regions of the universe that are very dense, that we expect to be very rich in terms of dark matter. And then this will favor to trigger annihilations between different dark matter particles or even decays. And out of the different possible channels that we can look at the standard, at the standard model particles that should be the result of this interaction, we are going to focus in gamma rays. And why? Gamma rays are not affected by the magnetic fields of the universe, so they travel directly from us, pointing back directly to the position of their origin. And also, at least for the local universe that is going to focus on, we do not expect a lot of absorption. So it really stands as a golden channel to perform the searches in WIMPs. So again, as Manuela was mentioning, now we need to face the reality and check where in the universe it will be the best kind of target to look for these WIMPs. So there are a few optimal conditions. One of you we already mentioned, like for example, we want to target a region in the universe which is high in dark matter density, because the flux that we expect in gamma rays with it coming from dark matter scales directly with the dark matter density profile in the case we're considering decay, and square if we are considering annihilation. But then we also want to target as the most massive possible nearby objects, because here we can see the dependence explicitly. The gamma ray induced dark matter flux scales directly with the mass of the object and decays with 1 over the distance squared. And then it will be magnificent if we are also able to find an object in which we do not expect any other kind of gamma ray emission. I will refer to this as a standard astrophysical gamma ray emission. However, this perfect object does not exist in nature. So we need to face what we see in the universe. As Manuela was mentioning before, one of the most studied targets in this sense has been the galactic center, but no, I'm not going to cover any of that in this talk. I'm going to go through the little difference and properties of other kind of objects that has also been widely used in the search for the WIMP. So at the right, we have galaxy cluster. At the left, we have some of the properties of dwarf spheroidal galaxies. As has been mentioned before, dwarf spheroidal galaxies are pressure-supported systems, so it's always a bit more difficult to try to obtain, from a phenomenological point of view, from an observational point of view, a measurement without a lot of uncertainty of its dark matter density profile. In the case of galaxy clusters have a very good point, and it's that galaxy clusters are the most massive gravitationally bound objects that we can find in the universe. So in the terms of the masses, there is nothing better that we can target than a galaxy cluster. However, they are farther away than the rest of the objects, like for example, dwarf spheroidal. So with this slide, what I'm really trying to say is that with each target that we select to pinpoint our searches, we need to be aware of the different caveats that we are going to consider in order to perform the analysis. And this leads me to the introduction of the dwarf irregular galaxies. Dwarf irregular galaxies are rotationally supported objects. They are isolated halos located in our local volume that can be found between 2.5 megaparsecs up to 10 megaparsecs, at least for now, and have masses in the range between the dwarf spheroidals and the galaxy clusters. No, they have been masses of 10 to the 8, 10 to the 10 solar masses. And they are expected to be star-forming galaxies, but let's go a little bit deeper into that. Sorry, so the fact that they are rotationally supported objects implies that we can measure the rotational curves. And from the measurement of the rotational curves, it has been proved that these objects are basically dark matter dominated along all of the ranges of the rotational curves. So we should be able to obtain dark matter density profiles directly from the observations. The fact that they are located in non-local volume means that they are close by enough. So this is also good in terms of the amount of gamma ray dark matter induced emission that we can expect from this object. And the fact that they have this range of masses also implies to us that a population of non-negligible population of substructures of these subhalos should be hosted in this kind of objects. And then about the caveat, about being star-forming galaxies and then having this other kind of gamma ray emission from this astrophysical source, there was this publication by Gamaldi et al. In 2017, where they studied 36, if I'm not mistaken, dwarf irregular galaxies and performed a theoretical study for obtaining the expected gamma ray emission from dark matter, assuming different dark matter models that you can see here represented with the green, blue, and yellow dots. And then with the purple dots, you can see the estimation made for the range of 100 MeVs to 100 GeVs of the flux expected from the star-forming galaxies from the star-forming rates. And from this picture, what is important to see is that the flux that we expect from this star-forming region is expected to be orders of magnitude below the one that we expect from dark matter, which in terms of the search for the wind, this is very good because this postulates the dwarf irregulars as a very good candidate to be taken into account. Now, indeed, that was the trigger to perform the first dark matter search in dwarf irregular galaxies. It was performed by the HES collaboration with the observation of WLM. Here is the paper that they published in 2021, so very recent work. Here I show you a bit of the characteristics of this dwarf irregular. As you can see, is far away from the galactic plane and also the galactic center, which should be good in terms of avoiding these very complicated regions in terms of the rest of astrophysical emissions. And here I report the results of the observation. As you can see, these are limits, so they did not detect dark matter from this object. They use the Wobble method, which is something that has been commonly and widely used in the community of imaging Earth Cherenkov telescopes. And the observation was only 18 hours. And for this very first observation, they assumed that WLM was a point-like source. And this is a very important point for what I'm going to explain right now. As you can see, the results were far away from the thermal relic cross-section that we expect from WIMPs. But again, we need to remind that this was the first search in dwarf irregular galaxies. It was just one irregular galaxy, and it was only observed 18 hours. So having this in mind, we then jump to Fermilab, because Fermilab was launched in 2008. So we have more than 15 years, I think it's already, right now, of gamma ray data. The good thing about Fermilab in this sense is that it's a whole sky survey and it produces an image of the whole sky every 3 hours. So this means that we already have gamma ray data to analyze and to search for WIMPs in dwarf irregular galaxies. So this is what we did in the paper that I'm going to present, which is Gamaldi et al., myself, and some more collaborators, like for example, Paolo Salucci here. And okay, let's go into detail. First of all, how do we compute the annihilation dark matter-induced gamma ray flux on an spherical object? This has been already covered by Manuela, but very briefly. We can always factorize between two parts. The first part, which is the particle physics model, this encloses all of the information of the spectral features that we expect from the dark matter signal. And in the second part is the astrophysical factor, which encapsulates all of the spatial information of the possible signal. In the case of the particle physics models, we are assuming, as I said before, weakly interacting massive particles. So for this, we will be using the spectrum already calculated by Cirelli et al. In 2012, including electroweak correction. And the main feature of this kind of spectra is that it's extremely dependent on the mass of the dark matter candidate, and also in the main interaction channel that we choose, meaning that, for example, for the quark for the bottom quarks, it will be different and have a more harder or softer spectrum than for example, W bosons. And for the astrophysical factor, this factor is directly degenerating with the general normalization of the flux, which is very important to take into account. And also because of this, quantifies the significance of the signal. And as you can see, the definition of the J factor is completely and directly defined by the dark matter density profiles. So what we will need to do is to perform a modeling of the dark matter density profiles, check the results that we see, and then go back to the Fermilab data and compare what we have. So out of the 36 dwarf irregular galaxies that were firstly analyzed in Gamaldi et al., this subset of objects were selected because basically we expect from them to have higher J factor than the rest of them, and also because they were located in observational good places, meaning that we try to avoid the locations close to the galactic plane and the galactic center. And for this applies for the three candidates, which are NGC 6822, IC10, WM, and IC 1613. And three new dwarf irregulars were analyzed for the first time in this paper, which are Phoenix, DDO 210, and DDO 216. Here you have the properties of each object, and then let's start with the modeling of the dark matter density profile. So as I said, we expect these objects to host a non-negligible amount of population of subhalos. So the best way that we found to take this into account was to split the dark matter density profile into two parts. The first part, when we will model the main halo of the dwarf irregulars, and the second one, when we will model a population of substructures with different benchmark models, obviously based on the results on embodied simulations. So let's start with the main halo. For the main halo, we, as I said before, have the results of the rotational curves for these objects. So our idea at the beginning was to directly perform a fit to these rotational curves using two different dark matter density profiles. One favoring what is being found in observations, which is a core dark matter profile following the Barker profile, but also try to fit an NFW profile in order to encapsulate the possible how our results will change in the future if the dark matter density profile was modeled in some other way, following this Moskowski-like. However, what happened is when we tried to fit the rotational curves to these Navarro-Frenkel-White profiles, we found some inconsistencies, meaning that we started to find non-physical values according to lambda CDM model for the concentration values. And this means a problem, and it's the fact that the rotational curves of these objects do not favor the Caspi Navarro-Frenkel-White profile. But still, we wanted to take it into account, again, in order to encapsulate all of the possible uncertainties that our results will have. So what we did, again, this is a first order approximation, was to assume that the mass of the Navarro-Frenkel-White profile was the same that the one that we fitted to these rotational curves with the Barker profile. Then select a concentration mass relation, of course, valid for the mass ranges of these objects, and from the standard relations, derive a Navarro-Frenkel-White profile for each of them, these 7 objects. Okay, and then now for the modeling of the substructure population. Two different things. We need to define also a dark matter profile for the subhalos, and as subhalos has not been found observationally, the only source of knowledge that we have are embodied simulations, and from embodied simulations, the only profile which is founded are Navarro-Finkenwild, and this is the one that we use. And then to model the population of substructures, we are going to split and to factorize between three different distributions. So the first one, which is how we distribute the subhalos in the main halo. And as we are considering spherical symmetry, this collapses to a subhalo radial distribution. Since we are using a Barker profile to model the main halo, it felt strange to base the whole modeling of the subhalo radial distribution in the embodied simulation. So we decided then, I will explain a little bit later, but we decided also to choose a density profile of Barker to represent the subhalo radial distribution and the Navarro-Finkenwild profile, which is very close to the results of the Via Láctea 2 simulation. Then we also have the distribution in mass, which is the subhalo mass function. These results come directly straight from embodied cosmological simulation. And the important part here is the alpha parameter, which sets the tilt of the power spectrum. Usually the values of alpha ranges between 1.9 and 2, being 1.9 more conservative values for the J factor that we are going to compute right now, and 2.0 will bring us higher J factors, we will see later. And finally, we need also to select a concentration mass relation for subhalos. In this case, we did not choose a specific concentration mass relation for subhalos because at this time it was not still available in the code that we are going to use to compute the J factor, which is the Clampy code, very well known in the community. Okay, so try to summary up. We have 7 different dwarf irregulars, and we are going to try to define 3 benchmark models in the terms of the modeling of dark matter. And this will try to encapsulate all the uncertainty that we have from the model of the substructures, meaning that we will have a mean model where we are not going to consider any kind of substructure. Then we have the MED model, which can be considered the best guess according to the recent result that we have. And then the max model, which is an educated upper bound of how much the substructure is able to contribute to the computation of the J factor. And this is the result that we have. So looking at the table, we can see that the dwarf irregular galaxies that have the highest J factor independently of the mean MED max model are NGC 6022, IC10, and WLM. And these are the values of the boost. The boost is defined with respect to the value of the J factor without taking into account the substructures. And it seems to be very well in concordance with what we expected from the concentration mass relation that we choose. But also very important here is the role that substructure plays in the terms of the extension of the object, because we have here the 2D dimensional templates of how the J factors are represented. So this will be all the spatial information of the signal that we expect, and we can see the big change from going from the mean model, which is not considering subhalos at all, to the MED and max Burke and max NFW. I want to stress the only model that uses NFW profile is the one which it's called max NFW. So now we have everything settled. Let's go to the data. We are using 11 years of Fermi data because at that point it was what it was available. In an energy range of analysis of 0.5 GeV to 1 TeV, and using 12 by 12 ROI, and integrating the benchmark models that have been developed by the Fermilab collaboration for the background components of the isotropic emission and also galactic intergalactic emission models. For this, we will apply a likelihood fit for each of the different dwarf irregular galaxies, but also combine the likelihood. And again, to stress that we are using as detection significance this TS model in which we will consider, detection if we go above 25. So we can see here that we do not get detection. We have some mild detection along WGM and NGC, but this is all pre-trials. So mostly possible, this is due to galactic diffuse emission. So we do not have signal, we present the results here. Here are 95% confidence level upper limit for individual dwarf irregular galaxies. We are very, very close to touching the thermal Rayleigh cross-section in the lowest part of the energy range. And we can see that the combined limits are basically led by the results of IC10, which is the best candidate in the terms of how much constraints we can get here. Okay, and since then, some more works has been done, but I do not have to go over this, so I will leave here the results that we obtained since 2021. Here's some studying the classification of these even gamma ray targets for taking into account velocity dependent and halo boosted dark matter annihilation, and also the latest results performing dark matter indirect searches using the Hawk facility. Okay, so I just hope that I have made my stand that dwarf irregular galaxies are something that we should consider for the future of WIMP searches. Thank you very much.